It is the second part of section 9.2, a simple network to classify handwritten digits. Here we'll see a network example. The problem of recognizing handwritten digits has two components, segmentation and classification. Segmentation is done in this way. Once digits are written in this way, then by using segmentation algorithms, we try to take parts in this way and save each one into an image. So here we'll focus on the classification algorithms, and also we'll use well-known public domain dataset, which is MNIST dataset collected by the NIST, U.S. National Institute of Standards and Technology. It has two parts. The first part contains 60,000 images for training. Of course, for each digit, it has 6,000 images. And for second part, it contains 10,000 images for test. And again, for each digit, it has 1,000 images. And each image is in 28 by 28 grayscale pixels. Let's see a simple feed-forward network. Now this is input layer and hidden layer and output layer. For input layer, we showed here a few. However, because the data has 28 by 20 gray pixels, the number of neurons in this input layer must be 28 squared, which is 784. And here we have 15 neurons in this hidden layer. And then now for output layer, we have 10 units. It is from 0 to 9, the digits. Okay. Now, once you design such network, then it's working reasonably well. So we'll try to understand why it is working well. And here we see the reason why it is working well and what the neural network will do. And here, to make it simple, we'll concentrate on the first up neuron, that one, and that is trying to decide the input digit is 0 or not, so that this one will here try to decide whether the input is 0. Now, to decide the input is 0, and the evidence will be weighted up, so that from this unit, the information comes here, and from second one also again, so that for all over 15 the units, the information is weighted up for this one. Of course, the other ones are also the same, but we are now concentrated on the first up neuron here. Okay. Now then, question is, what are those hidden neurons doing? So that what are they doing? So that for the sake of argument, we suppose the following. The first neuron in this hidden layer, for that one, is may try to detect whether or not an image like the following is present, so that in some portion of image, it's try to detect this kind of shape, so that once it is appearing this shape, then now the is fired along with strong value, and then send the signal to the upper layer strongly. That can be done along with heavily weighting input pixels and around this portion. And also for example, second neuron, again here is try to detect such a shape, and for the third one is trying to detect this one, and for the fourth here neuron, if it's trying to detect this portion, then once the image 0 comes, then all these neurons will be now firing. So that along with that here in the last moment here, this unit will decide that its input is 0, right? In this way, the complex neural networks work. Okay, now we'll see a little bit of detail. And dataset is given in this way: xi, yi. That is the image in each one is image in 28 by 28 grid pixels, and yi is from 0 to 9. But here yi must be written and along with the one-hot encoding. For example, if xi is about the number 2, then the yi can be made in this way. Here now, this position is for 0 and 1 and 2. So that in 2 position, the value is 1. For remaining portions, the value is 0. In this way, along with one-hot encoding, the label is set up. And the cost function is formulated in this way here for the label and activation of xi. So from xi, this is activation in the output layer, and the difference is measured along with here square sum, and here average them, so that here cost function is organized in this way. If we are using now gradient descent method, then and W and B, they will weight, and that is a bias, and W and B will be updated from the change in W and B. That is it is formulated in this way. Here minus gradient and scaled by learning rate. That is a standard formulation of gradient descent method, right? Okay, here now in order to compute the gradient of the objective function, we need to compute the gradient of each training input. So each imaging, we should be able to find the gradient separately. Then here we try to get averaging. Okay? And however, when the number of training input is very large, then for one update, averaging this all gradient is really expensive, and learning will be very slow. So that we may try to use a stochastic gradient descent, and for example, and for each one, you can update, or by using mini batch, so that a few of them, and you can get the averaging, and then this can be updated. That's the idea of stochastic gradient descent method, right? Okay. Here we'll see a little bit detail around stochastic gradient descent. Okay. First, we'll set a small number of training inputs, and M is way smaller than N. For example, you can choose about 10 or 20, so that by saying now M images, here we try to get, for each of them, we try to get gradient and then average them, right? Okay, over there is average them. And then that can be a good approximation of whole averaging, so that the mini batch algorithm is working very nicely. But the cost of this computation is much smaller than that one, right? In practice, you can choose batch size. In this case, that's M. It's 10 or 20 or 30, depending on here your preference, and you can choose some number. Okay. In practice, you can implement the stochastic gradient descent as follows. For each epoch means that once you access all the data set in the training set, all the data point in the training set, then we say we finished an epoch. And now each update is an iteration, so that an epoch has many iterations. But epoch means that the covering all the data points in the data set, so that for each epoch, first to shuffle the data set and random reordering, and for each M samples from the top, for each M samples will be used to update the weight and bias, so that go through down and from top to bottom. Then after finishing the epoch, and again we shuffle the data set and again do the same. That is how mini batch, the stochastic gradient method is implemented. Okay, here we have one example, and for the network to classify digits. Okay, that one is a little bit out of date. It's written in Python 2 and using Piano, and this one was well working. But if you try to run this code today, then you will spend some time to install the required the Python packages, so that here just try to see this example as a network example to classify digits, but don't try to run or don't try to implement this one. All it is showing that by using a small number of lines and a network, its complete network can be implemented if you are using Python. Python is quite flexible and here powerful computing language, so that it can be implemented very effectively. Let's see here, the network major part of the code is from here. Now go down, and then here it is now at 116 is finished. So there are some small portion extra saved. But anyway, and also inside of the algorithm, some comments and are included, so that eventually the whole network can be implemented using only about 150 lines in Python. So it is really powerful, and practically you'll use some very advanced packages like Keras and TensorFlow kind of some public packages. That is written for some various applications. However, if you try to make some implementation for the network from scratch, then you can finish it within only here 150 lines of Python. So it is not really complicated. Once you understand the logic, then you can do it quite effectively. Okay. By using the network.py, and also MNIST loader is separately written, and then after loading the data, and here after importing the network, and here now NNeuron is training, and then now here network is now designed in this way, so that input, okay, that one is basically input and hidden, and there's output. So just you are choosing 3 numbers, then it's automatically, now, along with one hidden layer, network is organized. If we put some more numbers here, then it's more hidden layers will be now added. So it is quite flexible. Even along with this small implementation, you can do here. Okay, now here number of epoch is 30, and patch size is 10, and yeta is okay. Yeta is chosen to be 3 for learning rate, and using these hyperparameters, now here stochastic gradient descent method is called, and then here we'll see the output. Okay, now out of 60,000, and for training 50,000 is used, and 10,000 is used for validation. So during updating after each epoch, by using this validation data, it is checking the accuracy. Because this one is not used for training, and here the accuracy is almost the same as using test data set. And by using this one is a validate, and then keep going, and then here later on by using this data set we try to get the test. Here we have validation accuracy, and after finishing one epoch, yet that epoch is 0 epoch is finished, and already about now 90% to accuracy, and after 30 epochs, and we have a little more than 94%. Okay, for this simple network, it is working in this way. And we have here accuracy comparisons. If you are using scikit-learn, and if you choose support vector machine, of course nonlinear support vector machine, and default one is along with Gaussian kernel, and along with that the accuracy will be here about 94% is almost the same as that one. Now if you tune well the support vector machine, then you can get about 98.5%. And also we learn this convolutional neural network, CNN, later. But if you have well-designed CNN, then the accuracy will become 99.79. So only it is missing 21 here, and we collected here those digits missed by CNN. And as you can see here, the images, even human intelligence cannot say what they are. Can you recognize these digits? But except those kind of things, the CNN got the right answer. So here we may say that the performance is close to human equivalent, and also we may say that it may be better in some directions. And so that here, as you can see here now, except these the missed ones, and everything else is correctly detected. And now if you see some more images, then also they are not easy to understand. However, now the network can understand it quite good. Okay. Here, model of the neural networks is here. That all the complexity be learned automatically from data, and simple algorithms can perform well for some problems. So that usually people say that here, rather than sophisticated algorithms, we may try to use a simple learning algorithm and good training data. The simple means that nowadays more or less around explainable or interpretable learning algorithm. But if you are trying to use, for example, TensorFlow, then it's not easy to understand the inside operations. And it's not easy also to debug once you have some issues. And rather than that, and try to use a simple algorithm and try to use really good training data, then it's better than using a sophisticated algorithm. Okay, and that's the end of the section. Thank you.